Good morning, everyone, and welcome to 4th day of session 100 of the EDP and Applied Mathematics Seminar. It's an honor for me to introduce to Professor Enrique Fernandez Cara, who is one of the strongest mathematicians in the area of control theory and partial differential equation today. Professor Fernandez Cara received his doctorate in 1981 in France under the guidance of Roland Glowinski, and currently he already oriented 13 PhD students and has 33 descendants. Likewise, his scientific production is high, having published 210 articles and approximately 5,570 citations. He is chief professor in the Department of Numerical Analysis and Differential Equation of the University of Seville. On this occasion, Professor Fernandez Cara will give the plenary entitled "And some inverse problem concerning the domain and or the coefficient of the partial differential equation." Welcome, Professor Fernandez Cara, and you can start.
Thank you very much, Juan. It's a pleasure to participate in this seminar, and I have to congratulate you for the success of this event, as well as the other members of the organizing committee, in particular Ana Dubova and Diego Souza. I will try to present in a schematic way some inverse problems that are related to the identification of the domain or the coefficients of the partial differential equations and the applications that we can solve with this analysis. Okay, this is the plan. The plan is to give first some general ideas, then to speak of elastography and the related inverse problems, and finally we'll try to present some very recent results on a domain identification problem for parabolic partial differential equation. Some words on inverse problems. In order to understand what is an inverse problem, it's a good idea to speak before of direct problems. In a direct problem, generally we have a set of data, and the data can be classified as D0 and D1. With this data, we get some results. The results are represented here by an arrow. And with the result, we have an observation. An observation can be understood as an additional information that we have on the problem. Contrarily, in the case of an inverse problem, it is assumed that some data are known, but some other data are unknown. So the known data are going to be denoted here by D0. And the goal is to recover, to find the other data, the unknown data, D1. And for this, usually, and in inverse problem, what we have as a help is the information. So the scheme is now that with some of the data that we had before, without the results, but with an additional information, we want to find the other data, D1. Usually, this is much more difficult than to solve a direct problem, among other reasons, because it is usually an ill-posed problem. The main questions that we have to solve frequently when we find an inverse problem can be listed as follows. First, we have the uniqueness problem. The uniqueness problem is this question. We want to know if, in the case in which two informations, I1 and I2, coincide, this implies or not that the unknown data, D11 and D12, also coincide. A stronger property is stability. Stability means that we can measure the distance between two unknown data, at least with a local estimate concerning the corresponding to informations I1 and I2. And of course, what is most interesting is the reconstruction problem. The reconstruction problem consists of computing at least a numerical approximation of D1 from I. So as an example, as a first example, let us consider the Calderon inverse problem. In the Calderon inverse problem, we have as data in principle omega, phi, and the coefficient A. And in the direct problem, the solution U to an elliptic system like this one produces an information, and the information is the Neumann data A multiplied by the normal derivative of U on a part gamma of the boundary. And for the inverse problem, contrarily, we don't know the coefficient A, but instead we know the additional information sigma, that is the Neumann data that is written here, on gamma for every phi that we fix here. So the question is whether or not we are able to find A such that all the solutions to problems like this satisfy the corresponding inequality that is here. This is a very well-known inverse problem, and there have been a lot of work during the decades. The most celebrated results are due to Sylvester, Ullmann, Astala, Pavarinta, etc. And the problem has a lot of applications to tomography, and as you probably know very well. This was an inverse problem in which the goal was to identify coefficient, to identify A. A second example is this one. In this problem, what we have to identify is the shape of the domain. I mean, for the direct problem, we are now with the knowledge of omega, phi, and D. D is a part of the set omega. And the information is, for example, the value of U on a small set with an omega included in omega. And the inverse problem is the question that we find when we do not know D. So the data are now omega and phi. We have as an additional information Z, that is the restriction of U on little omega, and we want to find D. This is a problem that has been considered by many researchers, as well as the previous one. It has also a lot of motivations in medicine, biology, etc. This is a scheme of the inverse problem concerning the determination, the identification of a domain. D is unknown. We know the values of U all over the boundary of omega, and we have an additional information on gamma. Okay, let me now speak of the first inverse problem concerning this talk. It can be called the Calderon-Lamé inverse problem. In the direct version of the problem, we have omega, capital T, that is the final time, a function phi, that is the Dirichlet value, is supposed to be the Dirichlet value of the unknown U, some initial data, U0 and U1, that correspond to the values of U and the derivative, time derivative of U at t equal to 0. And mu and lambda, that are functions on X and are written in this equation that is known as the Lamé system for U. This corresponds to the system, the elastic description of a system in which we have small displacement. The displacement are measured by U, and we have a volumic force on the right-hand side. We are fixing the values of U on the boundary, and we are also fixing the initial value of U and UT at initial time, t equal to 0. And in the direct problem, as before, in a similar case as before, the information is given by this expression. This expression is a kind of generalization of the normal derivative of U and can be interpreted as the normal stress produced by U, by the displacement U, once we apply F and we start from U0 and U1 at t equal to 0. Okay, this is the direct problem. It is well known. It can be solved with classical theory. And the inverse problem is found when we do not know mu and lambda. Mu and lambda are known, but instead we know lambda, we know the stress, the normal stress produced by U. So we want, I repeat, to find mu and lambda, the Lamé coefficients, such that the solution to A, the solution to this system, satisfies this equality. This has a lot of applications, in particular many medical fields, such as the detection and also the description of many kinds of cancers, arteriosclerosis, fibrosis, etc. From the medical viewpoint, we are doing the following. We fix an acoustic waves generator that is given by phi. We evaluate the stress, evaluate with the captor the stress that is given by lambda, and we apply a mathematical solver by means of which we are able to compute mu and lambda and then produce an image that is going to give us a description of the situation. There have been a lot of works since the 90s concerning this problem. And here you can see, as an example, elastogram image for a glioblastoma, which is a brain tumor that is indicated here, obtained by applying these techniques. So this is the system, this is the information, and the main questions that we can consider for the elastography in these problems are, first, uniqueness. I mean, if two observations, two additional informations coincide, does this mean that the Lamé coefficients are the same? Stability. I mean, can we measure in some space, in some normal space, the distance of the couples mu1, lambda 1, 2, mu2, lambda 2, in terms of the distance of lambda 1, capital lambda 1, capital lambda 2, and reconstruction. Reconstruction means to compute at least a numerical approximation. We cannot compute the exact values of mu and lambda from the information of capital lambda. There have been lots of researchers that have worked on these aspects for systems like this. Here's a list and no exhaustive list of some of them. What we have done. The first thing we have done is to prove a partial reconstruction result. I will try to explain this now. The partial reconstruction result says that under some hypothesis for the known data, F, Ft, U0, U1, and lambda, which is the additional information. Under some hypothesis, if we consider this problem in which we minimize the stress tensor produced by giving mu lambda to the observed capital lambda in this Hilbert space with respect to mu lambda, if we minimize this problem with respect to mu lambda in this set, I will come back to this set, to the definition of this set. Then for every R, for every capital R that is given here, there exists at least one solution that is called here mu R, R of the problem. This is a way to reformulate the reconstruction problem. I mean, imagine for a moment that this is forgot. We are not imposing these inequalities. Then what we are doing here is to minimize the distance of the stress produced for mu and lambda with no restriction, with no constraint to capital lambda. And if the inverse problem has a solution, the minimum is attained at the solution of the inverse problem. So this is a way to approximate to the reconstruction question, to give an answer to the reconstruction question for the inverse problem. Unfortunately, we have to work in a set like this, in which not only we have to limit the values of alpha and beta, which is very natural because mu and lambda are coefficients that have to satisfy hypotheses like this, assumptions like this, but we have also to limit, to put an estimate, to introduce a bound to the total variation of mu and lambda. Unfortunately, we have to work with bounded total variations for these coefficients. So mu and lambda cannot be arbitrary if we want to solve the problem. I will come back to this now. The idea of the proof is, in principle, easy. It's not too complicated. What we have to do is to prove that for a minimizing sequence, mu n and lambda n, we have conditions to take limits in the equations. And conditions to take limits in the equations, in fact, consist of proving that the gradient of un belongs to a complex set in the frame space L2 of capital Q. Q is the product of omega times 0t. This is the delicate point. This is, in fact, the main point of the proof. And using the fact that the total variation of mu and lambda are bounded by the same constant R, and some technical results, some Meyer's kind estimate, together with some interpolation results due to Tartar, we have been able to prove the compactness of these gradients, and then the fact that we can take limits in the equation and we can get a solution to the problem. As an additional result, we also have that this problem that is still is not the most desired problem, but this problem is also solvable. I mean, if we penalize the distance of the stress tensor to the observed values with a term of this kind, and epsilon can be arbitrarily small, then we can get a solution of this problem. And the question, of course, the pending question, of course, the important question is whether or not we have a similar result with no restriction or penalization on the total variations of the coefficients. Also, we have done the following. We have been able to get some successful numerical experiments. Let me show two of them. Of course, we have been able to approximate the equation. Here we have chosen a P1 5-element approximation corresponding to a domain. This is a case in which we have considered an omega, which is a circle, which is and the domain and the mesh are given there. And this is the problem that we are trying to solve. And we have taken for this test target mu equal to 10 here in the small ball D and 1 outside, and the same values of lambda. This corresponds to an idealized, more or less a standard tumor. In the tumor, the rigidity of the tumor is the rigidity of the region in which we find the tumor is about 10 or more times greater than the rigidity of the rest of the organ. So this difference between the tumor and the rest of the organ is what makes possible to apply elastography to detect the presence of a tumor. So this is the target. This is the target. And we have taken accordingly the value of lambda. And the value of lambda has been taken in the upper half boundary, the black part of the boundary here. And this is the observation that we have used to find from starting mu equal to 5 everywhere to find the solution via an appropriate algorithm. The algorithm that we have used is complicated. It's not too simple. I have not time here to explain, but it is a kind of augmented Lagrangian used in combination with limited memory quasi-Newton due to these authors, and it has worked very well here. After an appropriate number of computations of the cost, we have been able, with this amount of computation of the gradient of the cost that we are using here, we have got a final cost that is extremely small, and the figure that we find for the computed mu is just the same that we had for the target. And the same happens to lambda. We are also able to find the correct values of lambda. This is another test that has been solved with the same techniques. Here, the geometry is a little bit more complex because instead of one ball, we have two balls. Mu, it's assumed that we have two tumors in the organ, in the region, in omega. So we have taken again this, we have chosen again this as target, mu equal to 10 here and here, and 1 the remainder of omega. And with the accordingly computed information lambda, we have been able to start from mu equal to 5 and to get, after some work, the solution of the problem. This is what we have found for mu, and this is what we have found for lambda. And these two figures show the history of the computations. You see that the algorithm has converged relatively well, in the correct way, in both cases. There are a lot of questions that remain for the moment open. Some of them were related to the work in progress. For example, can we get the same kind of theoretical and numerical results for other linear elastic media, for other linear elastic partial differential equations? For example, in the case in which the tumor is not isotropic, we have to complicate the system. We don't have two Lamé coefficients, but many other coefficients. The system is again linear, but much more complicated. And we have not, for the moment, analyzed the situation. Three-dimensional problems are also important to consider here, because we are working at this moment on this, but it's not for the moment finished. We have noticed that the same kind of techniques are also able to give the solution of a three-dimensional tumor in a three-dimensional cavity. Okay, I'm now going to speak of a second problem. Second problem that concerns, contrarily to the previous one, domain identification. So the situation is different. Now we have a omega bounded open set as before, capital T as before, phi, which is again going to be the Dirichlet data corresponding to the solution U, and right-hand side, capital F, in general depending on X and T, and we assume that for some U satisfying this equation and these boundary conditions, corresponding to omega minus T, the partial derivative of U, the Neumann data corresponding to U on a part gamma of the boundary, are known. Okay. I want to emphasize the fact that in this system, there is no initial condition. So even for a direct problem related to this question, there's some information is missing. We don't have initial condition. And the inverse problem is to try to find D from this information where U is one of the solutions of the system in which the initial condition has been skipped. So this is what we want. We have some incomplete information, and we want to find the set D corresponding to this incomplete information. This is again the same picture as before, just to remember the situation. D is unknown. The equation has to be satisfied in omega minus D times 0T. Some boundary conditions, U equal to phi, are given the whole boundary of omega and also the whole boundary of D. And on a small part of the boundary of omega, gamma, we also know the normal derivative of U. But we do not know, I insist, we do not know the initial values, the values for U at time t equal to 0. Okay, this is a result that we have obtained very recently in collaboration with Jonia Price, Anna Lubova, and Masahiro Yamamoto, that says the following. Let us assume for simplicity that phi is equal to 0. Similar result can be obtained with different phi, but let's take for simplicity phi equal to 0. And assume that D1, D2 are simply connected and simply connected open sets, completely connected in included in omega. And let us assume, this is the main hypothesis, that F is of this kind, has separate values, separate variables, is of the form F of X times mu of T, where we assume that F is not identically equal to 0, but it is equal to 0 in D1 and D2, and mu is a characteristic function. Mu is equal to 1 for T between 0 and T naught, and equal to 0 for T greater than T naught. Okay? This is the main assumption that I'm going to impose here. I will come back to some possible extension of this assumption, but for the moment I assume this. Then we have uniqueness for this problem. I mean, if for some solution of the corresponding system to D1 and the corresponding system to D2, we have the coincidence of the normal derivatives on gamma times 0T, in this case, we necessarily have D1 equal to D2. Okay? Even in this case, in which the information that we should have for the Dirac problem would be incomplete, even in this case, we are able to prove uniqueness. Let me give some comments and extensions of this result, and then I will try to explain very briefly how it can be proved. First, let's say that a more realistic assumption of F is to say that there exists a common set omega naught, again, completely included in omega, such that D1 and D2 are subsets of omega naught, and F is equal to 0 in omega naught. Since D1 and D2 are in principle unknown, this is a more realistic assumption that says, in fact, that we have to have, we must have F equal to 0 in D1 and D2. Second comment, it is interesting to see that the theorem implies that D1 is equal to D2. So U1 is equal to E2 by virtue of the unique continuation. We have U1 and U2 solutions of the same equation in the same set, because D1 is equal to D2, and satisfy the same boundary conditions, and there are normal derivatives coincide on the part of the boundary of omega. So necessarily U1 is equal to E2, and from backwards uniqueness, we also have that U1 and U2 coincide at time t equal to 0. So the result says not only that D1 is equal to D2, but also that the initial values corresponding to these two functions, U1 and U2, coincide. There's an interesting question, probably hard question, that is the following. Can we prove the stability of D and the values of U at time t equal to 0 with respect to the observed quantities derivative of U on gamma? And we have an estimate of the distance of D1 to D2 and the initial values of U1 and U2 in the left-hand side and the right-hand and the left-hand side, and something depending on the difference of the observed quantities on the right-hand side. It seems to be hard in view of the arguments that needed to prove this result. Let me also say that together with this result, we can also prove a similar result in which we have a boundary source and internal observation. I mean, here we have an internal or right-hand side observation. Sorry. We have used an internal source, an internal source corresponding to F and mu, and the observation has been on the boundary, on part of the boundary. We can do the contrary. We can prove that with the boundary source and internal observation, a uniqueness result is also possible to be proved, okay? So the source and the observation play a role that is in some sense symmetric. Also, we have the possibility to extend the result, not only for the heat equation, but also for more general parabolic equations with regular coefficients, with other boundary conditions, etc. And it would be interesting, we are working on this, but for the moment it's not finished, to prove a kind of result, some result of the same kind, or a similar kind, for linear hyperbolic partial differential equations. Of course, this is not easy. It's not so easy because, in fact, we can extend directly the result to this frame, among other reasons, because for linear hyperbolic partial differential equations, as you all know, we need some time to make information reach from one point to another. More comments and more extensions. Well, we can extend, as I said, the situation to non-zero functions f. F has to be analytical, or at least satisfy a unique continuation property, as we are going to see soon in the proof, in order to apply the same argument. But it is possible to work with regular f and to obtain more or less the same kind of uniqueness result. The result is also true for other mu, and this includes not only characteristics functions, but also delta functions, which is interesting can be interesting from the viewpoint of applications. And there is a known question, open question, as far as I know, that is the following. What happens in the case in which f is more general, is not of separate variable kind? Are we able to obtain something similar with the arguments that I'm going to present in a moment? More extensions. This is interesting from the viewpoint of applications. The results can be obtained also, more or less the same techniques, for Stokes, linearized Boussinesq, linearized Aldrich, etc., for many kinds of linear systems concerning fluids. This is connected to the determination of a known obstacle in fluid. Even we can work in all these systems with n-1 observations on gamma. I mean, we do not need to know the n-dimensional vector sigma times n on the boundary, on part of the boundary gamma, but what we need is n-1 projection of these quantities on the boundary. It is interesting that in the case of the Stokes problem, and n equal to 3, an open question is whether it is possible to obtain the same result by the knowledge of just one n-2, just one component of the additional information. This is open. It is an interesting question because for systems like Stokes, a situation like this does not lead necessarily to unique continuation. But even without unique continuation, the question remains. And of course, it would be very interesting to know if the result is also true for Navier-Stokes or other variant of the Navier-Stokes system, including nonlinear terms. Let me give an idea of the proof. The main ideas are based on unique continuation and analyticity in time. So in the first part of the proof, we fix D1, D2. We say that G is the complementary of D1 union D2. And we prove very easily, using unique continuation, that the difference U1 minus U2 is 0 in this set. It is very easy to see that this happens because unique continuation applies to these equations. So outside D1 union U2, we have U1 equal to U2. And the question is what happens inside D1. For example, what happens in D2 minus D1. So in the second part, we assume that D1 is different from D2, and we say that E is open and non-empty, a part of omega open and non-empty, that is included in the complementary of D1, whose boundary is a subset of the union of the boundaries. It is a situation like this one. E is the set, And what we want to prove is we have a contradiction because we have assumed that D1 is different from D2. And the contradiction comes from the fact that if we introduce U1 just in E, and we say that E naught is a part of E, this function is analytical. This is the main tool that we can use here in order to deduce the contradiction. H is analytical, saying we work a little and we see that this other function constructed with built with the help of H is also analytical, and in view of the particular mu that we have taken on the right-hand side and particular f that we have taken on the right-hand side, we arrive at an absurd, because at the same time we have to have u equal to constant, and the fact that u is equal to constant says that f is equal to 0. The details are given in the paper that we have in preparation at this moment, but the result is true. Let me say that there are other arguments and results connected to this problem that gave more or less the semi-uniqueness theory. In particular, we can use Cardinal estimates and even another tools such as the Hanna principle of the problem. Let me end by telling you that we are working now on the reconstruction. I mean, the idea is now to find D, and of course, you know, the initial value of U from the observation. The observation is called here beta. And for the reformulation, we have chosen something very similar to what we have done before. We again minimize this quantity in an appropriate set, and the results concerning this approach to the reconstruction in progress and will appear soon. In fact, we have also done some time ago things of this kind for similar elliptic problems in collaboration with Pythagoras, Carvalho, and others. And we are now trying to apply the same techniques based on the method of fundamental solutions to this setting. This is a list of references that contain all the things I have been speaking of. And thank you very much for your attention.
Thank you so much, Professor Enrique Fernandez Cara, for your amazing plenary. Now is the time for question. Any question or commentary? This audio is open. Any question? I have a curiosity, Professor. It is possible to study inverse problem, unique instability or reconstruction, in equation with no local terms, parabolic or hyperbolic?
Good question. If we speak of domain identification problems like this one, this can be done under, at least what I know is the following. This can be done under the condition that the equation has to be linear, because for the moment we are not able to apply the same techniques to nonlinear problems. The equation has to be linear and has to satisfy a unique continuation property. So, for example, if you add here a coefficient multiplied by the integral of u, the answer is yes, because the equation is linear. You have an additional term in which you have a coefficient multiplied by integral in space of u, and the unique continuation property is satisfied. So it is much more difficult to consider non-linear or semi-linear problems. It is much more difficult. And in any case, the technique that we are using here asks as an almost essential condition to have unique continuation. We need a unique continuation to start the argument. We need a unique continuation to apply the argument, the complementary of D1 or union D2. But, of course, for this kind of problems, there are many things that can be done.
Thank you, Professor. Other question or commentary, chat, English, Spanish, Portuguese? Well, if there are no more questions, thank you again, Dr. Professor Enrique Fernandez Cara, for your amazing plenary, and see you in other opportunity.
Okay, thank you very much. Thank you.